You're lying on the savanna grass, hours old, naked, can't lift your own head. 10 feet away, a wildebeest calf is already sprinting from lions. A zebra foal is running with the herd. You can't even roll over. You won't walk for a year. You need someone protecting you every hour of every day for years. Nature kills things this defenseless fast. Here's the thing nobody tells you. Your helplessness isn't a bug. It's the most calculated risk evolution ever made. Let's actually look at how bad it is. That wildebeest calf standing 10 feet away from you, it was on its feet within about 6 minutes of being born. Wobbly, but standing. Within a day, it's keeping pace with a herd that can outrun a lion. An elephant calf stands within an hour and is walking alongside its mother by nightfall. Even other primates, chimpanzees, your closest living relatives, are born with a brain already close to 40% of its adult size. And by their first birthday, that brain is pushing 80% of the way there. You, on the other hand, showed up with a brain that's roughly a quarter of its final size. A quarter! It won't hit 90% of adult size until you're about 5 years old, and it keeps rewiring itself for another 2 decades after that. No horns, no fur, no ability to grip, no capacity to flee. Just a skull-shaped promissory note and about 18 years to make good on it. Here's why this should bother you. On a savanna, slow is a death sentence. Every prey species out there front-loads its survival, spends everything it has before birth so it can run the second it's born. You did the opposite. You spent almost nothing before birth, which means for years afterward, you're the easiest kill on the entire continent. If any other species tried this strategy, it would have been erased in a single bad season. So why weren't you? For a long time, anthropology had a tidy answer, and it's the one you've probably heard, even if you didn't know it had a name.
In 1960, anthropologist Sherwood Washburn looked at this exact puzzle and called it the obstetrical dilemma. The logic goes like this. Walking upright on 2 legs works best with narrow pelvises. Narrow hips make for an efficient stride. But a big brain needs a big skull to grow inside. Those 2 pressures point in opposite directions, and something has to lose. Washburn's answer was that childbirth loses. Nature's workaround, in his telling, was to evict the baby early, kick it out of the womb before the skull gets too big to clear the exit, leaving you born in a state scientists actually call secondary altriciality.
Which is just a formal way of saying your baby is basically still a fetus that happens to be able to breathe air. For decades, that was the whole story. It's clean, it's dramatic, it's got a villain, your own mother's skeleton, and it got taught in anthropology classrooms for 2 generations straight. But here's where it gets interesting. The dilemma has a hole in it, and the hole was found when looking for the wrong-shaped evidence. In 2012, anthropologist Holly Dunsworth and her colleagues at the University of Rhode Island went looking for proof that wider hips actually cost women something when they walk or run. If Washburn's theory was right, women with birth canals wide enough to deliver a more developed baby should move less efficiently. Dunsworth's team published their findings in the Proceedings of National Academy of Sciences, and the locomotor penalty simply wasn't there. No meaningful cost to walking, no meaningful cost to running. The bony highway your baby has to travel down could plausibly have evolved a bit wider, penalty-free, and just kept babies inside longer, cooking a little more before showing up. So if the exit door isn't actually the bottleneck, what is? The bottleneck is your mother's metabolism, not her bones. This is the energetics of gestation and growth hypothesis. And here's the mechanism. A pregnant body can only sustain a certain rate of energy output before it starts to break down under the load, somewhere in the neighborhood of twice her normal resting metabolic rate. A growing fetus, meanwhile, has energy demands that climb almost exponentially as the 3rd trimester goes on. Picture your mother's body like a phone charger with a hard current limit, and picture you in utero as a battery whose draw keeps climbing every week. To be fair, even this explanation isn't the final word. Some of the metabolic data behind it comes from small sample sizes, and follow-up studies have found the picture messier than the original hypothesis suggested. The honest answer is that both mechanical limits and energy limits are probably operating at once, and researchers are still arguing about the mix. Which, if you're the kind of person who wants a clean textbook answer, is annoying. But here's the real question hiding underneath both explanations, mechanical or metabolic. Why does your brain need so much energy in the first place that it forces an early exit at all? Your brain is about 2% of your total body weight. At rest, it eats roughly a fifth of your entire energy budget, sometimes more. Gram for gram, it burns through fuel at a rate no other organ in your body comes close to matching. Anthropologists Leslie Aiello and Peter Wheeler named this the expensive tissue hypothesis back in the mid-90s, and the number gets even wilder once you're not looking at an adult. A 2014 study led by biological anthropologist Christopher Kuzawa, Northwestern University, tracked exactly when the brain's energy costs peak across childhood, and it isn't at birth, when the brain is relatively largest compared to the body. It peaks around age 4 or 5. At that age, your brain is consuming roughly 2/3, 66% of your entire resting energy budget. 2 out of every 3 calories a 4-year-old burns while sitting completely still are being poured straight into wiring a skull. Think about what that actually means for a small, defenseless body on an open plane. It's like trying to run a supercomputer off a phone charger, while also expecting that same charger to power a car. Something has to give. And what gives in a human child is almost everything else: muscle development, coordination, self-sufficiency, the ability to flee, forage, or fight. The energy that a wildebeest calf spends building strong legs in its first 6 minutes of life, you are spending building synapses instead. You are not behind. You made a trade. Here's where the story spirals back to the grass for a second, because this is the moment that reframes everything. That baby, lying there, unable to lift her own head, she isn't malfunctioning. She is mid-construction on the single most expensive piece of biological equipment any mammal has ever attempted to build inside one lifetime. And construction doesn't pause just because there's a predator in the grass. But here's the problem with a project this expensive. No one animal can fund it alone.
Which opens the real question. If raising a brain like this costs more energy than a single mother's body can generate, who pays the rest of the bill? This is where human life history does something no other social mammal does. Most social mammals, wolves, elephants, other primates, move through exactly 2 pre-adult stages: infancy, then straight into a juvenile period where the young animal is basically a smaller, faster-learning adult. Anthropologists Barry Bogan and John Locke mapped out something different in humans. We insert 2 extra stages nowhere else on the mammal family tree wears in quite this form.
First, childhood. A stretch of roughly 4 years between weaning and the juvenile period, when a kid still can't feed or protect itself, but no longer nurses. Second, adolescence. Another 8 years or so between the juvenile period and full adulthood. Neither stage is decoration. Both are extended windows of protected time, purpose-built so an unfinished brain can keep being wired without interruption while someone else handles the business of staying alive. Which brings us back to the money question. Primatologist and anthropologist Sarah Hrdy did the math on this in her book, Mothers and Others. Her estimate, raising a single human child from birth to full nutritional independence costs somewhere around 13 million calories. 13 million, far more than one healthy adult woman foraging entirely on her own could ever generate, especially since she's usually pregnant with or nursing the next child, well before the current one can feed itself. Hrdy's point is blunt. No ape in evolutionary history has ever produced offspring this costly, this slow, and this dependent without serious outside help. Something had to change about how the bill got paid, where the whole species-level bet on big brains simply doesn't clear.
So here's how it got paid. Hominins solved this the way any group solves an expense too large for one person. They spread it out. Anthropologists call it cooperative breeding or alloparenting. Fathers, older siblings, aunts, unrelated group members, all chipping in calories and protection for children that weren't strictly theirs to raise. And one group of caregivers shows up again and again in the data with an outsized role: grandmothers. Anthropologist Kristen Hawkes at the University of Utah found some of the clearest evidence for this doing field work with the Hadza, a hunter-gatherer community in Tanzania.
She noticed that Hadza postmenopausal women were remarkably productive foragers, spending long hours digging out tubers buried in rocky ground, food that was far too tough and deep for a young child to extract on their own. When Hawkes and her colleagues tracked children's growth against who was doing the foraging, a pattern jumped out. A weaned child's weight tracked closely with how hard their mother worked, right up until the mother had another baby. After that, the correlation shifted. The weaned child's weight started tracking with how hard their grandmother worked instead. That single shift matters more than it sounds like it should. It meant mothers could wean children earlier and have the next baby sooner without those older weaned kids starving in the gap, because grandma was quietly footing part of the 13 million calorie bill. Some researchers now argue this is a major reason humans, alone among the great apes, evolved decades of healthy life after menopause. In chimpanzees and gorillas, females generally die around the same time their fertility runs out. In humans, grandmothering may have paid for itself so consistently, generation after generation, that long life after menopause simply stuck around as a trait, meaning your childhood may not just have required grandmothers. It may have helped invent them, evolutionarily speaking. So let's close the loop all the way back to where this started. You are lying on that grass, unable to lift your head, 10 feet from a wildebeest calf that is already running for its life. And none of that means you lost the evolutionary bet. You were never competing on the same terms. That calf spent everything it had before birth so it could sprint within minutes and never really improve much beyond that. You spent almost nothing before birth on purpose so you could keep spending for 18 more years on something no calf, no foal, or elephant will ever need or get. A mind assembled slowly enough, expensively enough, and with enough outside investment from people who weren't required to give it, that it never really finishes growing at all. Every extra year of your helplessness wasn't evolution failing to patch a flaw. It was evolution's receipt for the most expensive object it has ever tried to build inside a single body. One so costly that it had to recruit fathers, siblings, and grandmothers just to cover the invoice. And in doing so, it may have built the entire architecture of human cooperation as a byproduct. The instinct to feed a child that isn't yours. The instinct to protect the stranger's kid on instinct alone. That might not be a separate story from your helplessness on the savanna grass. It might be the only reason that helplessness ever survived long enough to become you. Every other species on that grass made a bet on speed. Yours was the only one that bet on time and on each other.